Hey everybody, let's spend a little bit of time talking about network solids. Now, network solids are really neat things, okay? And so network solids seem to be things that would bond covalently, but they don't have properties of covalent bonds, and that makes them really kind of neat. Kind of the big examples are the allotropes of carbon, like diamond and graphite, which we'll talk about in our examples here. And then there's silica, which is the common name for silicon dioxide. And so there's a lot of neat network solids out there that give rise to really neat properties. So, and so I guess in terms of like a learning, a learning thing or like a shortcut to know if something's a network solid, what I'll say is if it's acting really weird, it's probably because it's a network solid. Okay, so let me get rid of this little thing. And so what makes a network solid different from just a covalent compound is that network solids are going to form these long chains of compounds. And so using the of elements together, so the idea is like carbon, when carbon is graphite, what it forms are these really funny long chains of carbon that kind of do this thing here. And so the only element that's in it is carbon, okay, provided that I draw all these things correctly. But if the only thing that's in it is carbon, then it's an element, but they're all bonded together, so they're not moving. These atoms aren't moving independently from each other. And so if we remember the particulate theory, we think about ionic compounds as having a really strong intermolecular force because the positive and the negative attract each other, and then it's like, there it is. It's pretty cool. And so sodium chloride, like, that has a very high boiling point, melting point, because it's really attracted to each other. These sodiums and chlorides are really attracted to each other. Well, now when we have a network solid where all these guys are bonded together, that network solid is really kind of neat because it's not attracted. It's not an intermolecular force. It's an actual bond. So when we talk about melting points and boiling points of these guys, I mean, they're going to be skyrocket because you have to heat it up enough to break the bond, as opposed to just forcing the atoms to come apart because of an intermolecular attraction, an intermolecular force. Okay, and so that really explains these long chains, and that there's no individual molecules in these covalent, or these network solids. Okay, like silicon dioxide forms these crazy long chains of silicon and oxygen together that just aren't able to be broken, and that means that they're going to have like absurdly high melting and boiling points. And some of the other things is that they are very hard. Some of the hardest substances on Earth. For example, diamond. Diamond is all carbon, and diamond is so hard because you're unable to break the bonds that are holding the atoms together. Okay, and so that makes that makes diamond really hard. Okay, same with silicon dioxide. Okay, silica is very hard and it has a really high melting point because of the way that these seemingly covalent molecules are just bonded together. Okay, now these sorts of things, just so you know, don't happen often. Okay, but when they do happen, they're very easy to kind of point out, because you'll see like which one, why does silicon dioxide have a boiling point of 2800 degrees Celsius? which one, and then, sodium chloride has a boiling point of 800 degrees Celsius. And you have to explain that. Well, this, you should immediately say, well, that's because it's a network solid. Okay, it's a covalent compound, but it's a network solid. So that's kind of neat. It kind of adds to our breadth of knowledge about what happens with these molecules. Okay, so I'm going to move forward here. And so this is exactly what we're talking about. Okay, and this gives me a chance actually to bring up some neat vocabulary. Diamond and graphite are kind of the same. They're the same thing. They're both carbon. And so when we find two different things in nature that are made of the same element, so we have carbon, diamond, carbon, graphite, that word is called allotropes. It's the same element, but found in different forms. Okay, and so it's kind of like isotopes, but it's an atom, it's an element that's found in different physical forms. And so you can see here the representation of all of these different network solids here, all these atoms. And so what makes carbon diamond, what makes diamond so much stronger is because you can see it's all bonded together. It's a huge network of bonds and atoms coming together. What makes graphite so slippery? For those of you who don't know, graphite is one of the best lubricants ever. Well, if you can see, it's bonded together. The atoms are bonded together here, and that's kind of neat. But you can tell that here, and I'll do it in red, is that there's no bonding between this sheet of carbon. And so what that does is it allows these things to move like this as a big sheet, and this one to move as a big sheet, because it would rather slide across each other than and independently from the sheet above it than it would to break the bonds that are in the sheet itself. So graphite really becomes a kind of neat little lubricant. So, and so here are some of the sample problems, okay, or here's a sample problem. And this sort of sample problem is more of a theory sample problem. It says, based on the structure of graphite, explain why it has a high melting point. Okay, well, it has a high melting point because it's and this is circular reasoning, because it's a network solid. Okay, so that's the answer to this, which means that it is a covalently bonded compound that needs a lot of energy to break the bonds between atoms. Okay, so again, the idea here is that graphite is this huge chain of of carbon atoms, just all bonded together, and those aren't going to come apart very easily. Okay, so what are some of the intermolecular forces that exist? Well, you could say that it is that a covalent bond exists, but that's not really an intermolecular force. And so if we're going to really answer this question, we probably should go back to the previous slide. Okay. And the intermolecular forces are really just the forces that exist between the sheets here, because that's a covalent bond, and a bond is a bond, not a force. Okay, well, I guess technically it's a force, but we in chemistry delineate between the two. Okay, so what is the only force that exists here? Well, the only force that exists between like elements, or elements that are exactly the same, is London dispersion forces. So what holds these sheets together is a really weak London dispersion force, which means that they're even more so going to slide past each other. Okay. Notice diamond doesn't do that. It's all covalently bonded, and so it's all really hard. So, really the only force that exists is London dispersion forces, unless you're going to count the covalent bonding as a force. I wouldn't, but that doesn't mean that it's not what I would actually. That doesn't mean that other people would. Okay, so that's what a network solid is, and have a great day.